Okay, hello everyone, and welcome to General Chemistry 101. Today we are going to talk about Chapter 7, which is the quantum theory and electronic structures of atoms. So let me just start with a short story here about quantum mechanics. And actually, by the end of the 19th century, scientists were reaching a stage of arrogance that they discovered everything. They thought they discovered actually everything, and in the sense that they have the classical laws of physics. It can explain everything basically, including the subatomic particles like the protons and neutrons and electrons. So they thought they just need to apply the classical laws of Newton's and the classical physics laws that they have on these subatomic particles, and that's it. And by the end, actually, at the years like 1850, 1900, people were reluctant to go into even to science schools because they thought, okay, what to study? There's nothing anymore to discover. They discovered everything. But they realized that the classical physics laws, they actually do not apply to these subatomic particles like the atoms and protons and these small things. It took a long time to actually realize, and even longer time to accept that the properties of atoms and molecules are not governed by the same physical laws as larger objects. And by that time, there were some phenomena, like natural phenomena, that the science didn't explain. And people start to think that there might be something hidden. And then the quantum theory came in to play. The first scientist who worked in the quantum theory and actually brought us the idea of the quanta, and he is the father of quantum mechanics, is Max Planck. Max Planck was, this is, I think he has a picture of him. Yeah, this is Max Planck. Max Planck is a German scientist, and you know that in Germany now we have the Max Planck Institute, one of the greatest scientific institutions on earth. Max Planck in the 1900s, he discovered that atoms and molecules actually emit energy only in certain discrete quantities, and he called them quanta, because before that, people thought that atoms and molecules can emit energy at any wavelength. But Planck, he came up with the idea that with the quanta, which is a discrete amount of energy, and he proposed that atoms and molecules, it can emit energy at certain levels, like 1, 2, 3, 4, 5, not 1 point, and forgetting about the digits, so it's not 1.5 or 2.3. He just said that the energy can be emitted in quantums, in whole numbers of energies. He called them quanta, and this was the dawn of the quantum theory or the quantum mechanics theory. The quantum theory is kind of a complicated theory actually. I'm not going to go into details of it. So at this level of chemistry, we are just going to study the results of quantum theory. So of course, quantum, for people who study it, I really enjoy quantum mechanics and I teach it to higher levels. It's a kind of a crazy theory, but it works. So it provides you with good results, and we still use it till now to explain our chemistry. So quantum theory is the theoretical basis of modern physics that explain the nature and behavior of matter and energy on atomic and subatomic levels. And Planck's discoveries contradicted previous assumptions that energy is continuous and that any amount of energy could be released in a relation process. So in order to start with Planck's idea, we just need to refresh your mind with the properties of waves. So as you might study in physics, a wave is consisted of a kind of an amplitude and a wavelength. So this can apply to the waves of sound or waves of light. So the wavelength in the wave is the distance between the two identical points in the successive waves. So this is like the length between two waves. We have also the amplitude or the height of the wave. This is the vertical distance from the middle of the wave to the peak of the length. We have also the frequency, which is a very important factor here. The frequency is the number of waves that pass through a particle point in 1 second. So you imagine yourself standing at one point of this wave, and the wave is moving, and you're just counting how many waves are moving by second, and this is called the frequency, and it's measured in hertz. Hertz is the unit for frequency. Also, we have a fourth thing, which is the speed. The speed is basically equal to the wavelength times the frequency. So the wavelength in this science is denoted lambda. Lambda is a Greek letter for wavelength. And we have also the frequency, which is a nu, nu. This is not V, this is nu, which is a Latin letter, also a Greek letter referring to the frequency. So the speed, of course, of the waves depends on what wave we're talking about. Are we talking about speeds wave or air or, sorry, light? It also depends on the medium that the wave is traveling on. What we are interested in actually in physics and chemistry is the speed of light, okay, which is the speed of the electromagnetic wave. So light, if I ask you what is light, you might provide different answers. But in physics, actually, we define light as a combination of the electrical field and magnetic field components. So it has two components. The electrical field is in the vertical component, and the magnetic field is in the X component or horizontal component. And each one has wave properties, okay? And they travel, these waves, they move fast, they travel so fast at the speed of light. This is what the definition of light in physics. So the most important thing about light is that the speed of light, which is c in vacuum, which is very high speed, 3 times 10 to the 8 meter per second, is actually lambda times mu. So this is a major component of physics of light, which contributes to the quantum mechanics as well. So c is equal lambda nu, where c is the speed of light, is a fixed number. It's not only actually a constant number in physics so far. And lambda is the wavelength of the wave, and nu is the frequency of the wave. So from that you can actually calculate this. Okay, so as you might know, we have the electromagnetic spectrum, or the electromagnetic radiation, which is light. Now, our daily life tells us that we have the sunlight, which, you know, it's composed of the spectrum, we call it in Arabic. Is that it goes from the violet into the red. This is the visible light that our eyes are designed to observe during our daily life, okay? These are the colors that we can see. But the light itself is actually, the visible region of the light is only a small part of the light. Light itself contains many other types of lights. For example, with a wavelength shorter than 400 nanometers, we have the UV light, and with wavelength longer than 700 nanometers, we have the IR light, which is the infrared light that used in our remote controls and in IR cameras and so on. And also, so the electromagnetic light actually, it extends over a wide range of wavelengths. It starts with the gamma rays. The gamma rays, they have very, very short wavelengths, okay? They're very dangerous, they're very strong. They are caused by explosions in stars and so on. A little bit weaker, but it's still strong, is the X-rays. The X-rays, they have also short wavelengths. It's 10 to the minus 1 nanometer, okay? We have the UV, as we said, it's in a range of 10 nanometers, 100 nanometers, something like that. And then the visible region is in the middle here, which is the one that we see as human beings. It extends between around 380 nanometer to around 750 nanometers, actually, within this range. And then after that, we have some longer wavelength electromagnetic radiations, like the microwave, the UV, and the TV, and all of these wavelengths. Now, as you go from left to right here in this scale, the wavelength increases, as you see here. So it starts very small or very short, and it goes longer. but the frequency takes an opposite direction here. So for gamma rays, the wavelength is too short, but the frequency is too high. Okay, the frequency is too high. That means it's very dangerous. Okay, and it's very strong. For TV and radio waves, the wavelength is too long, and the frequency is too small. And this is obvious here from this equation. When you see C is equal lambda nu, that means lambda nu is equal to constant. So as lambda increases, nu of course decreases. So this question is so straightforward. The wavelength of a green light from a traffic signal is centered at 522 nanometer. What is the frequency of this radiation? So you are provided with the wavelength and you ask for the frequency. So this is straightforward. C is equal lambda nu. So nu is equal C over lambda. And lambda we are giving it as 522 nanometer. The problem with this question is when you apply the C, the speed of light is in the units of meter per second, and this one, the lambda is provided in nanometer, so these units are not talking to themselves. We need to change the nanometer to meter. Of course, 1 meter is 10 to the power 9. 1 meter is equal 10 to the power 9 nanometer, or 1 nanometer is 10 to the power 9 minus 9 meter. So you change the unit, you say 522 nanometer multiplied by the unit factor, which is 1 times 10 to the minus 9 meter, is equal 1 nanometer, and the answer is 5.22 times 10 to the minus 7 meter, which makes sense, it's a small number. Then lambda in this case is equal to the speed of light divided by lambda, and you obtain a value of 5.75 times 10 to the power 14. 1 over second is the unit, because the meter goes with the meter out, and you are leaving with the unit is equal 1 over second. Now this 1 over second, we call it hertz. The 1 over second is equal hertz. So as you see here, the number is too big, 5.75 times 10 to the power 14. That's in the range of actually gigahertz. Okay, it's the millions of hertz, because this is kind of a short wavelength. So this is the frequency you're expecting out of this wavelength. There is also example 7.2 in the book, so please take a look at that as well. 7.2 in the book. Take a look at this after you finish. Now, so let's go back to what Planck proposed. So one of the things that dazzles humans' minds and scientists' minds in the end of the 19th century is actually what we call the ultraviolet catastrophe. Without going into details, the UV spectrum of some atoms, it's not continuous as the scientists thought. So classical physics, it actually can explain the UV spectrum of some atoms in some region. But when you go to the UV region, their results failed badly. And this is called the ultraviolet catastrophe, or the problem of the ultraviolet spectrum for atoms. When Planck came in, he proposed the idea of quantization. That means energy can transmit only in discrete numbers, 1, 2, 3, 4, 5. When the scientists applied Planck's idea to the hydrogen atom, it worked. And there was a big success for Planck's theory, and he actually won the Nobel Prize for that. It's not only Planck who took the Nobel. Everybody who worked in quantum mechanics, Planck, Heisenberg, Einstein, Schrodinger, every one of them awarded the Nobel Prize for his achievements. So classical physics failed badly to explain the ultraviolet catastrophe, and that's a problem of classical physics. So when I say classical physics, I refer to Newton's law of motions and the classical laws that we learned in school. But Planck demonstrated that atoms and molecules could emit or absorb energy only in discrete quantities, like small packages of bundles, and he called it quanta. So Planck was actually the first man to came up with the word quantum. This is where quantum theory name came in. So quantum is the smallest quantity of energy that can be emitted or absorbed in the form of electromagnetic radiation. And Planck, of course, he came up with a very important relationship that we all know, which is the energy. That energy that we are talking about is equal h times nu, where h is constant. Okay, And so the energy is a multiples of frequencies. It's not a continuous thing. It is a discrete. It can travel only in packets or a discrete numbers. Where this so the energy of a single quantum of energy is given by h nu, where nu is the frequency and h is Planck's constant, which equal to 6.63 times 10 to the minus 34 joule dot second. You don't have to memorize this number, but we're going to use it to calculate energy. So frequency is related to energy directly. So if you go back to this electromagnetic spectrum here that one we're talking about, if we are talking about gamma rays is very dangerous, is very strong. The frequency of the gamma rays, remember, it's very high, therefore its energy is so high. But when you go to the visible spectrum, for example, the visible spectrum is in the middle. It has also short wavelength and maybe high frequencies, but its energy emitted by this visible spectrum is much less than the X-rays and the gamma rays, so it's not very harmful. But you see here, when you go to the left of the visible spectrum, you have the UV, which is the ultraviolet, which has a higher energy than the visible, and that's why maybe ultraviolet light kind of harmful to human beings' skin, and it might cause cancer. When you're talking about radio waves and TV waves, those are burning with lower frequencies, very low frequencies, okay, very long wavelengths, and therefore a very low amount of energy, so they don't actually cause any harm to the human health, if they are used, of course, in moderate amounts. So after Planck's, Niels Bohr came in, and Bohr, he used Planck's idea to explain the line spectrum of atoms. So when you emit light, let's say on one atom, like let's say sodium, what you observe is one line of a spectrum, and that was not understood by the scientists at that time. So what Bohr said, Bohr used Planck's idea to explain the hydrogen atom spectrum. And this leads to a line spectrum of atoms, and the line spectrum are light emission only at specific wavelengths. So here, if you imagine, hydrogen, of course, contains one proton and one electron, and it's the easiest atom to study. So if you shine some energy, H and U, on this electron, the electron can go from the ground state, what we call the ground state, to an excited state. A ground state is the minimum energy level where the electron usually is sitting, okay? When you give energy to this electron, the energy excites, okay? It moves, if you use the word, you cannot say the electron moves, but just to get the idea here. So the electron goes or moves into a higher level of energy, which we call an excited state. Of course, the electron cannot stay there for a long time. It goes down quickly, and the amount of energy from between the energy difference between the ground state and the excited state can be emitted as light, and you can detect this light, and because this amount is fixed, then you're expecting a line spectrum. Now this idea here proposed by Bohr, it was not there before the quantum theory. So this is a new idea here, that the energy levels in atoms, it's sitting in levels 1, 2, 3, 4, and the energy can go only from level 0 to level 1 or 2 or 3. It cannot go, let's say, between these levels. So Bohr actually, so this is here the theory or what's happening in Bohr. If you bring me a lamp, let's say, and this lamp you fill it with hydrogen, okay, and you emit some light on this lamp, or you turn this lamp on, the light that comes out of this lamp, it goes to a prism, and from the prism, you know that if you do this with sunlight, you're gonna have the whole full spectrum. You will see all the colors. If you did this in school, in your childhood, if you bring a prism and you split the sunlight, you will observe the whole colorful spectrum that we know. But what happens in hydrogen, for hydrogen light, the hydrogen that comes from hydrogen, you will see only some lines. You don't see the full colors. You only see a few lines. So the reason of that is because the hydrogen atoms electronic levels is actually divided into discrete numbers 1, 2, 3, 4. Not so energy can travel between 1 to 2 or 1 to 3 or 1 to 4 and not between these levels. So it's not continuous, it's line spectrum. This is the line emission spectrum of hydrogen atom, the expected one. You will see a number, you will see a line at around 400 and then maybe 420 and then 500 and 480 and so on. So you don't see colors at every wavelength, but at discrete wavelengths. Now why is that? It's because if you see in this here, for example, we call these energy levels n. N equals 1, n equals 2, n equals 3, 4, 5, and 6, and 7, and so on. So when you excite the hydrogen atom, like you give it some light, the electrons will jump into excited states, but when they go back, they can go back only from 2 to 1, or 3 to 1, or 4 to 1, or 5 to 1, and so on. When the electron goes back, it emits some energy that is equal to the difference between 1 to 2, or 1 to 3, or 1 to 4. And therefore, you see these lines in the hydrogen spectrum. You don't actually see a continuous spectrum. And that was a big discovery, a big news for Niels Bohr, that he actually won the Nobel Prize for that. And that was the introduction for quantum mechanics. The only problem with Niels Bohr theory is that it fails actually, because it only worked for hydrogen, unfortunately. So everything Bohr spoke about worked beautiful for hydrogen, but it failed to work with every other atom than hydrogen. So it failed for lithium and helium and carbon and all the atoms that we know. However, Bohr did his job, and we scientists after Bohr used his ideas to improve the idea. This is another this is a representation of Bohr theory again. We have the nucleus, which is in the middle. We have n equals 1, which is the first orbit, and the second orbit, n equals 2, and n equals 3, and so on. Now, the problem with Bohr's theory is that, according to classical physics laws, an electron orbiting the nucleus would quickly collide with the nucleus and attach itself to the proton. This is the problem with Bohr's idea and the old ideas, is that if you have a nucleus which is positive and there is an electron that is orbiting the nucleus, and بلف حولها, okay, rotating. The problem with this is the electron is negative and the proton is positive. So if you keep this negative moving, it will lose energy at some point. And when it loses energy, its orbit decreases until it hits the nucleus, and this will vanish the atom. This is the end of the atom. That's a problem with this Bohr's theory. That's the problem. It doesn't work. If this electron is rotating and it emits some energy, that means it's going to lose some energy. So it will slow down. When it slows down, it's going to rotate slower and slower and slower. Okay? So you'll have kind of a spiral movement here. Well, at the end, it will hit the nucleus, and that will be the end of this atom. So Bohr explained why this does not happen by hypothesizing that the electron is allowed to occupy only certain orbits of specific energies. Energies of the electron are quantized. This is what Bohr proposed to solve this problem. And then he said electrons can only have specific quantized energy levels. And light is emitted as the electron moves from one energy level to a lower energy. So this is what Bohr proposed to solve this problem. He said the electrons are only allowed to occupy certain orbitals. It cannot occupy orbitals in between. So it can either be in 1 or 2 or 3. And it moves from 1 to 2 or 2 to 3 or 3 to 4 or the other way. But it cannot go, to, let's say, in between. The electron cannot sit in between 1 and 1.5 or 2.3 or 3.6, let's say. So suddenly the electron moves from one orbit to another. And the energy difference between the two is equal to minus RH multiplied by 1 square, where RH is called the Rydberg constant. It's equal to 2.18 times 10 to the minus 18 joule. And N is the principal quantum number, which was 123. And from that, you can calculate actually the energy difference between two levels. Now, when you apply this equation, it provides you very good results for hydrogen atom. But the problem is when you apply this to some other atoms, unfortunately, it does not work. So Bohr's theory only works for hydrogen atom, and that's the problem with Bohr's theory. Now here we define the ground state, which is the ground level of energy, for n equals 1. Okay, this is the minimum level of energy where the electrons are usually sitting in Bohr's theory. And any other levels, which is 2, 3, and 4, these are called excited states or excited levels. Okay, they are higher in energy, and electrons can jump to these levels only when you shine light on them. Okay, or when the atom is taking some energy, some external source of energy. So we can also represent Bohr's theory by this diagram here, where you have the n equals 1, it's the first step, and n equals 2, and n equals 3, 4, and so on. So, and the atoms cannot actually move in between, they just jump from one level to another. Okay. Now, if you want to calculate delta E actually for one electron, it's actually minus RH times 1 over n initial square minus 1 over n final square. You can obtain the delta E by using this equation, and we're going to solve a problem for this very soon, which is this one. So here it says, what is the wavelength of a proton in nanometer emitted during a transition from the n initial n final equals n initial equal 5 state to the n initial equals 2 state in the hydrogen atoms. So here I just want to draw your attention to something. So if you have n equals 1 and n equals 2, so when electron jumps from here to there, so n initial in this case is 1 and n final is equal to, and this is called absorption, because the electron is taking energy to go from 1 to 2. Okay, but if the electron is going down now, so here n initial is 2 and n final is 1, and this is called emission. That means the electron will emit the light back to the environment. So usually we start with absorption. The electron absorbs, and how the electron absorbs is we give it some energy. Okay, you give it some energy, which is equal to h nu. The electron will take the energy, will jump into n equals 2. That's the absorption. So in this case, n initial is 1 and n final is 2. But the emission here, when it goes back from n equals 2 to n equals 1, now your initial is 2 and your final is 1, and this is called emission. Now in this question here, it says calculate the wavelength, not the energy, for an electron that is emitting, is going from 5 to 2, so that's emission, okay? From 5 to 2. So initial is 5 and n final is 2. So we apply this equation, delta E is equal to RH 1 over n initial square minus n final square. So we put the numbers, delta E is equal to 2.18 times 10 to the minus 18 joule. This is the formula I'm using here, RH is 1 multiplied by 1 over 5 square minus 1 over 2 square, because n initial here is 5 and n final is 2. This is very important to do for energy. Now 1 over 5 square is a big number, minus 1 over 2 square is 1 over 4. So this is 1 over 25 minus 1 over 4. So you will get a negative value of this. And therefore delta E is equal minus 4.58 times 10 to the minus 19 joule. This is kind of a negative, and we learned in chapter 6, this is kind of exothermic. Exothermic, then it means the energy will go out of the system. And this is exactly what you're expecting from this. When you emit the energy, okay, when the electron is going from n equals a higher level to a lower level, the energy will be emitted. So that's what we learned, that means the system is giving you the energy, that means it's exothermic. So this is exothermic exothermic process. So emission is always exothermic, and absorption is always endothermic. Okay. Now the question does not ask you to actually calculate the energy. He asks you to calculate the wavelengths. So we calculate the energy. We know that the energy is equal H in nu. So H in nu, that means the nu is equal to delta E over H. If you supply this into the C equals lambda nu equation, you will get that C is equal lambda over delta E over H. And therefore lambda is equal CH over delta E. I'm just rearranging the equations here to calculate the lambda. If this is too difficult for you, you can calculate the nu from delta E in one step. You can calculate the frequency from delta E because delta E is equal H in nu. So using the Planck's constant, you can find the nu first, and then you supply it into the other equation. You can do it easily, but I have done it in one step by formulating a formula to find lambda, and lambda is equal CH over delta E, and therefore I'm putting all the numbers here. Just make sure that the units are cancelled out, because if they don't, you will get a problem. So C is the speed of light, 3 times 10 to the power 8 meter per second, times the Planck's constant, which is 6.65 times 10 to the minus 34 joule dot second, divided by delta E, the one we calculate, which is 4.58 times 10 to the minus 19 joule. And in this case, I took the absolute value of the energy because lambda cannot be negative. Lambda is always a positive number. So I just changed the sign here, and I took the absolute value of energy, and I found lambda to be 4.34 times 10 to the minus 7 meters, which is, if you convert that to nanometer, it's going to be 434 nanometer, and this one is a very reasonable number for a line spectrum of hydrogen. So as you see here, the lambda that we obtained from this equation that relates to the movement of the electron from n equals 5 to n equals 2 is only one number, okay? And that's the beauty of Bohr's theory, that he managed to predict the line spectrum of hydrogen. Actually, this number is very close to the experimental value. The problem with Bohr's, as I said, it only works for hydrogen atom, unfortunately, and it does not work for any other atoms. Now, there is a section in the book that is cancelled, which speaks about what is the quantum theory and what is the wave function and all that. Now, this section is cancelled. You can read it at home if you like. You can also watch videos about quantum theory from YouTube. You can learn a lot. It's a really fun thing to learn about quantum mechanics and the beauty of it and the different crazy things about it. But in this course, we're not going to get into the details of this. We're just going to take the results of quantum mechanics and apply it to our case. Now, before I continue, does anybody have a question on the previous thing? Anybody needs a question? Can you open the mic and ask me, please? Because I'm reading your chat windows here. I don't understand what's going on. Anybody has a question?
Doctor, in the previous example, 7.4,
yeah.
Can you just explain it a bit slower? I did not get it.
Okay, sure. Yeah, we can cover it.
And also,
yes.
In this example, where did we get the 2.18 into 10 power 18?
Oh, this is okay. So this is small. Okay, this is the formula that we used. Yeah, Lena, is it Lena?
Yes.
Lena, this is the formula that we use. Delta E is equal RH, which is 1 over 1 n initial square minus 1 over n final square. And RH is the Rydberg constant. هي معرف هون. Rydberg بيساوي 2.18 times 10 to the minus 19 joule. Minus 18 joule. ماشي؟ So this is a constant. هذا بيكون يعني معطى بالامتحان. Don't memorize it. This is a constant, which is 2.18 times 10 to the minus 18 joule. ماشي? And then n initial here is, this is n initial 5 and this is n final. So I'm just applying the rules here, which is delta E is equal RH open bracket 1 over n initial square minus n over final square. So RH is given، هذا معطى بيكون بالسؤال 1 over 5 square minus 1n square. So this, I'm just putting the numbers here. So when you do the math, you will find this answer, minus 4.58 times 10 to the minus 19. And this is exothermic as I explained. Then you can actually take this all out. You want to continue an easy way. You say delta E, we found delta E to be equal to minus 4.58 times 10 to the minus 19. صح؟ جوا مظبوط؟ Yes. So delta E is equal to H nu, okay, and C equals lambda nu. So we are after lambda. The question is asking for lambda. We know that H is also Planck's constant. We know what, 6.63 times 10. So delta E is equal 6.63 times 10 to the minus 34 joule dot second times nu. So we can find nu, and then we apply it here, okay? So mu is equal delta E over H, صح? Which is equal 4. I just want to change the sign, so I don't get negative number. 919 joule dot second على H اللي هي 6.63 times 10 to the minus 34 34, okay? Joule dot second, sorry, joule delta E. This one is in joules, and this one is in joule dot second. So the joules goes with the joules, and therefore you will have an answer for mu. You can calculate that at home. I don't want to calculate it, but you will have the answer as 1 over second or hertz. And then you can continue saying that C is equal lambda nu. يعني lambda بتساوي C على nu وتساوي 3.80 times 10 to the power 8 meter per second على الانسر اللي انت يعني الجواب النيو اللي انت طلعته هون عوضه هنا بيطلع عندك الجواب مباشرة. As I said, Bohr did a beautiful job. He won the Nobel Prize for this, but his idea worked only for hydrogen atom. So then came up Schrodinger. Schrodinger was a German scientist, was so smart. He came up with something called the Schrodinger equation, okay? Of course, before that, there was also Heisenberg, who also contributed to the science of quantum mechanics. So the quantum mechanics, it's a new theory. It's very complicated, okay? You don't study it at first year of university. You have to finish your calculus courses first and all of your chemistry courses before you get to quantum mechanics. But the quantum mechanics came up with the idea of a wave function, psi. This symbol called psi, psi, okay? This psi, the wave function, it's a new function that describes the movement of electrons. This is written psi, but it's spelled as psi, but said as psi. يعني بنحكي psi مش psi. For this wave function, it describes the wave movement of electrons in a much complicated way than classical physics. And the wave function, when you put it in the Schrodinger equation, it's a complicated equation that is the source of whole the quantum mechanics, and كل quantum mechanics مبنية عليها. From you solve the Schrodinger equation, you get the quantum numbers. And this is what we are going to study. So this is the short story of quantum mechanics. Quantum mechanics uses the wave function, which is psi, to solve the Schrodinger equation, and the solution of the Schrodinger equation will give you the quantum numbers and also will give you the energies. The quantum numbers that we obtain from quantum mechanics are 4. We have the principal quantum number, which is n. which is the main quantum numbers, and this one is the same that Bohr proposed, n equals 0, 1, sorry, n equals 1, 2, 3, 4, etc. N cannot be 0. But we have also other 3 quantum numbers that came up from quantum mechanics. Nobody knows about these quantum numbers before. The next one is angular quantum number. It's called L. And we have also the magnetic quantum number, which is ML. And we have the spin quantum number, which is MS. Now the first one, I'm going to talk about the first one only in this chapter, in this lecture. And on next lecture, inshallah, we're going to continue. So the N quantum number, it takes values of 1, 2, 3, 4. It cannot be 0. And this is called the principal quantum number. And this is the one we know from Bohr's theory. So there is nothing new here. But the new thing that N, this N, the value of the N determines the energy of the orbital. So the further the orbital, the word orbital is the level that we're talking about, and we call it an orbital. The farther away the orbital from the nucleus, the higher the energy, okay? So for example, the 1s orbital, which has an n equals 1, is closer to the nucleus than n equals 2, and closer to the nucleus than n equals 3. So as n grows, the distance from the nucleus grows, and also the energy of the orbital becomes bigger. So I think we're running out of time, so let's stop here, and inshallah on the next lecture we are going to continue. Thank you so much for listening, and have a beautiful day. Please don't forget to sign your name.